So hello, ninth grade. Welcome back. We're going to continue in chapter 12, talking about functions and their graphs today. I have to tell you, I had a lot of anxiety about this, but the Lord is so good. Last night in my sleep, I woke up and I was kind of thinking about this and lots of other lessons I'm doing for other classes, and just felt a lot of anxiety and nervousness, and I just felt a verse come to mind that the Lord your God is with you wherever you go. And I pray that's a comfort to you guys in the midst of all this mess, these corona times. He is with us, and I'm just so thankful for that. Hope you all know that He's with you as well. Did get my hair cut yesterday, and Mother and Father came over with bandanas on. They live pretty close. They're 82 and 86, so we went to the backyard. We stayed outside, sanitized all the tools. I tried not to breathe. But anyway, it was so funny. My dad, he's watching, and oh, honey, you're cutting it too short. She doesn't wear it that short. So then my mother, oh, well, I can't glue it back on now. So anyway, it is what it is. We proceed. It'll grow back. All right, so let's talk about functions and their graphs. Those of you who had me last year for pre-algebra, we talked about this before, and we used what was called the vertical line test to look at a graph and see if we could determine if it was a function. Because remember, every x can only be matched with one and only one y. Each person can be one and only one height. And so if there were two, we would have it would touch in two different places on our vertical line. So if this line is our graph, we're going to go from left to right with a vertical line. And do y'all see that there's no place at which that line touches this vertical line more than one time, right? Every spot, it's just touching it at one place. So this passes the vertical line test. That's a function. Okay, now this one, if I go left to right here, oh my goodness, there's lots of spots where this graph is touching my vertical line more than once. So this is not a function. Now this is a step function. We haven't graphed these yet, but you're supposed to be aware that they happen. And this is like from here to here, this part's open, but this part's closed. So as you see, if we go left to right, it's only touching at these circles. This is dark and this is open, so that's legit. Now if this were colored in at two different spots, it would be no. But because it's open here, closed here, it's only touching at one point. I hope that makes sense to all of you. All right, so try this, A, B, and C on page 543 and see what we have. All right, so for A, this is an upside down parabola. And remember I told you, theoretically, as these go out, they're never going to go straight down. Okay, so they're going out and widening, right? Getting farther apart as it continues to go out. So this one is a yes. There's no place that this is going to cross more than once, because these are not going straight down. They're continuing to go out as they go down, okay? Ever so slightly. So A is, yes, it is a function, not touching the vertical line more than once. B, however, lots of places where it touches twice. So this is a no. And C, this part right here, bunch of times. So no, because of that right there. Okay? All right, so now let's look at example 2. Now example 2 asks us, is the relation x equals absolute value of y a function? Well, what we would want to do is make a table, and 2 points determine a line, but in any of these other functions, you want to do about 4 or 5 points and make sure that you've considered some different cases. So in this case, we're going to let y, we're going to give y some values. Let's let y be 0 and 1 and negative 1. Because if I plugged in 0, okay, the absolute value of 0, oh, not time for you to go. Absolute value of 0 is 0, okay? If I plug in 1, the absolute value of 1 would be 1. If I plugged in negative 1, the absolute value of negative 1 would be 1. Uh-oh. 1 can't be matched up with two different y's. So no, we right away concluded that it is not a function. Okay? How about example 3? It says, is y equals 3x a function? Okay? Well, we can plug in some values. This time, because I'll let x be 0, 3 times 0. If I let x be 1, 3 times 1 is 3. If I let x be negative 1, negative 3. And as you see, this one is not good. It's going to be a function because every x is getting matched to a different y. So this one is, yes, a function. All right, so let's try the D, E, and F. Again, stop the video. You do your work. I'll do mine. Okay, so with D, this was in slope-intercept form, so I could just do a graph if I wanted and determine, oh, I know that's linear, and sure enough, that's going to pass the vertical line test. I could also do a table and plug in for x, okay, and see that none of my x's are matching up with different y's, so this one is a function. Now, x equals y squared. Okay, now in this case, I want to plug in values for y. So 0 getting squared is 0. 1 getting squared is 1. Negative 1 getting squared is 1. Uh-oh, so what happens here? I've got 1 matched up with two different y's. Can't do this. This is a no. Okay? But if it's flipped around, y equals x squared, that would be okay. So you have to be careful which values you're plugging in. This one, y equals the absolute value of x. I'm going to plug in values for x. 0, absolute value of 0, 0. If I plug in 1, the absolute value of 1 is 1. Plug in negative 1, absolute value is 1, and so forth. So here, every x is matched with its own y. Okay, two people can be the same height. This is legit, not the other way around. So this one is also a yes. All right, now the next thing that we want to do here is to determine the domain of a function. So turn the page, 544, and it says here, when a function is defined by an equation and the domain of the function is not stated, we assume the domain is all real numbers, okay? But there are two conditions that you need to be careful of. So let me show you example 4. We have f of x is 2x minus 5, okay? This is just like saying y equals 2x minus 5. We could plug in values. We could graph this with slope-intercept. So the domain here is all reals. There's no, like, anything you can't have In other words, we don't have like a 0 in the denominator. We don't have a square root that's a negative. So if you don't have any difficult conditions, your domain is going to be all reals. Example 5, g of x equals 1 over x minus 2. All right, here we have a variable in the denominator. We're not allowed to let our denominator be 0. So this domain would be all reals except for x cannot be 2. If x were 2, 2 minus 2 is 0. Can't have that. So x cannot be 2. Any other number in the universe is fine. But I can't let the numbers I plug in give me a 0 in the denominator. The other condition I have to watch out for is example 6. I have h of x equals the square root of, I think it's x plus 6. Okay? I'm also, in the real number system, not allowed to let this value of the radicand be a negative. It can be 0, so x could be negative 6. That would be okay. But I can't let x be negative 7. Negative 7 plus 6 would be negative 1. Can't have a negative under the radical. I can't let x be negative 10 or negative 20. So what you do in this case is you say x plus 6 has to be greater than or equal to 0. Whatever's under here, you write that radicand greater than or equal to 0, and you solve it, which in this case, I'd subtract 6. And this is my domain, okay? Any number greater than or equal to negative 6 will work. I could plug in negative 5. That's greater than negative 6. Negative 5 plus 6 is 1. The square root of 1 is 1. That's okay. All right? So, for the domain, you're either going to have all reals, or you're going to make sure that you don't have a 0 in the denominator. You're going to make sure radicals are greater than or equal to 0, or radicands. Okay? So those are the only difficult conditions. If you don't have a denominator with variables, you don't have a radical, then you just say all reals for your domain. All right, so take a look then at your practice, G, H, and I. Try this, G, H, and I. Stop the tape. You do that. For G, no difficult situation, that's all reals for your domain. Any value can be plugged in to get an answer. Right here, I cannot let this equal 0. So, x cannot be a negative 5, right? Negative 5 plus 5 would be 0. Can't let that happen. And down here, I take my radicand, I set it greater than or equal to 0, has to be 0 or above, and I solve by adding 1, and so this is my domain for, try this I think it is, G, H, and I. All right, and then the last part, example 7 and 8 are on graphing the functions. Now, you all know how to do linear functions, so example 8 should be pretty simple. Okay, this is example 8, just reviewing it. H of x equals 2x minus 1. Remember, your function can be written like this. You can call that h of x y. This is in slope-intercept. I start at my y-intercept. My slope is 2 over 1, so I'll go up 2 and run to the right. That gives me 2 points. There's the graph. Okay, so example 8 was pretty simple. Example 7 says that g of x equals absolute value of x. All right? Well, that's like saying y equals absolute value of x, so we'll make a little table, give it a few values. All right, so if I let x be 0, the absolute value of 0 is 0. If I let x be 1, absolute value be 1. If I let x be negative 1, 1. If I let x be 2, the absolute value of 2 is 2. If I plugged in negative 2 right here, 2 comes out. So when I plot these, everybody, it'll be 0, 0, 1, 1, negative 1, 1, 2, 2, negative 2, 2, and this makes a V shape. So isn't that cool? The absolute value function makes a V shape. I love it. All right. So let's do J, K, and L. Last time for today, stop the tape, do your graph. Okay, so for J, the absolute value of x, take away 1. So I made a table. If I let x be 0, 0 minus 1, negative 1. If I let x be 1, the absolute value of 1 is 1, take away 1, 0. If I let x be negative 1, negative 1 under the absolute value sign comes out as 1, take away 1, 0. 2. 2 minus 1 is 1. Absolute value of negative 2, 2, take away 1, 1. So when I plot this, it's still a V shape, but it has actually just gone down. That's what that minus 1 does. It just moves that graph down. So if this were minus 2, this graph would go down 2 units. If this were plus 3, it would come up here. It would do like that. So it takes the parent graph, the absolute value, and kind of shifts it up or down depending on what number that is. So that's a fun fact. Makes life easier on yourself if you know that. All right, K, that was a linear function, right? If I let g of x be y equals negative x plus 4, I could start at my y-intercept. This slope is negative 1, so I write it as negative 1 over 1. So from my starting point, go down 1, run 1, always run to the right, connect your dots. You could also do a table, that's fine. You can call that g of x, doesn't matter. And you'll still get the same deal. And then h of x is the opposite of the absolute value. So it's interesting. This one, instead of going up with absolute value, the minus makes it go down. And if you learn these shortcuts, that's great. It makes it a lot easier. That you don't have to do a table all the time. But I did one. And so you'll see if I plugged in, say 1, then 1 comes out, but I want the opposite. Therefore, plugging in 1 for x gives me -1 for y, or h of x. Okay? So you can see how I did those. All right, this was a lot. You may want to watch this again. You may want to read the lesson carefully, study the examples on your own. They may present it better than I do. So, but refer to RenWeb, do your assignment. Call me for FaceTime if you need some help. God bless you all.